Let's rest here for a while, and let something unfold slowly. There's no need to focus too carefully, no need to hold on to what comes next. This is simply a place where ideas can drift by, like clouds passing across a wide, empty sky. You don't need to learn anything tonight. You don't need to remember. If your mind begins to wander, let it. If sleep finds you halfway through a sentence, that's exactly as it should be. We're going to talk about something tonight. Something scientific. Something calm. About the internet. About encryption. About the invisible locks that keep our digital world secure. And about a kind of computer, still mostly theoretical, still years away, that might one day change how those locks work. But there's no urgency here. No crisis unfolding in real time. Just ideas, moving slowly, like water over smooth stones. So settle in. Let your breathing slow, let your thoughts loosen, and let this wash over you, gently, without effort. Long pause. The internet as we know it today is held together by invisible threads. Not wires alone, though those exist. Not servers, though they hum quietly in distant rooms. But by something more abstract. Something mathematical. Locks. Digital locks. Locks built not from metal, but from numbers. From problems so difficult, so vast, that no ordinary computer could ever solve them in time. Problems designed to take longer than lifetimes, longer than civilizations. Problems that would outlast the patience of anyone trying to break them. And these locks, these mathematical locks, they keep things safe. They keep your messages private. They keep your bank accounts secure. They keep software updates authentic and websites trustworthy. They do this quietly, without fanfare, without you ever noticing. And for decades, this system has worked. Beautifully, silently, like a watch ticking in a room no one enters. But there's a question now, a slow question. A question that doesn't demand an answer today or tomorrow, but one that scientists think about, carefully, methodically. What if a new kind of computer arrived? A quantum computer. A machine that doesn't just run faster, but runs differently. A machine that could, in theory, solve some of those hard problems, not in lifetimes, but in hours. Would the internet fall apart? Would encryption collapse overnight? Would everything we've built simply stop working? The answer, and this is where we can rest because the answer is calm, is no. Not quite. Not in the way you might imagine. Pause. Let's sit with that for a moment. The internet would not instantly fall over. The digital world would not vanish. There would be no sudden darkness, but something would change, slowly, methodically. Certain locks, specific kinds of locks, would become vulnerable, and so, for years now, scientists and engineers have been preparing, designing new locks, testing them, standardizing them, planning a migration that is already underway, not because the threat is here, but because the threat could be here someday. And when you're building systems meant to last decades, you plan ahead. You move slowly, carefully, without panic. And that's the story we're going to tell tonight. A story about locks and keys, about problems that are hard and problems that might become easy, about a future that is uncertain but not frightening, a future where cryptography evolves, as it always has, to meet new challenges. But we'll take our time. We'll let each idea settle before moving to the next, and if you drift off along the way, well, the ideas will still be here, waiting, patient, like stones at the bottom of a quiet stream. Long pause. So let's begin, slowly, with the idea of a lock built from something you cannot see, cannot touch, a lock made of mathematics, the internet, this vast sprawling network of computers, servers, devices, and signals, relies on these mathematical locks. It relies on them constantly, every time you visit a website, every time you send a message, every time software updates on your phone. Behind the scenes, invisibly, your device is using these locks, and the locks are designed around a simple, elegant principle. Certain mathematical problems are easy in one direction, but extraordinarily hard in the other. Easy to lock, hard to unlock, unless you have the key. This asymmetry, this one-way difficulty, is what makes the whole system work, and it's been working for decades, quietly, reliably, like a river flowing in its bed, unnoticed, uninterrupted. Pause. There are two main layers to this system, two kinds of cryptography working together. The first layer is called public key cryptography. Let that phrase sit for a moment. Public key cryptography. It sounds technical, and it is, but the idea is simple. It's a system where you can share a key publicly, openly, with anyone, and yet no one can use that key to unlock your secrets. Only you, with a private key that you keep hidden, can do that. This is what allows your computer to talk to a bank server or to a website without anyone eavesdropping on that conversation. It's what allows you to agree on a shared secret across an insecure network without ever meeting in person. And the mathematics behind this layer, the locks, the keys, the problems, are built on things like factoring large numbers, or computing discrete logarithms, or working with elliptic curves. These are problems that, for large enough numbers, would take a classical computer, an ordinary computer, an unimaginable amount of time to solve, time measured, not in years, but in ages, in eons, and so they are safe, for now. Pause. The second layer is called symmetric cryptography. This is the workhorse, the engine that actually encrypts your data once the secret key has been agreed upon. It's faster, more efficient, less mathematically exotic. Algorithms like AES, like CHA-20, names that don't matter much right now, but systems that run billions of times per day, encrypting emails, video calls, downloads, backups. This layer doesn't rely on hard mathematical problems in the same way. It relies on something simpler, a key that is so long, so random, that guessing it, even trying every possible combination, would take longer than the universe has existed. A brute force search through a space so vast it might as well be infinite. And so this, layer 2, is safe, for now. Pause. These two layers work together. Public key cryptography to establish a secret, symmetric cryptography to protect the data itself. It's a dance, a handshake, a protocol. And it happens every time you see that little lock icon in your browser, every time your phone connects to a secure network, every time a software update is downloaded and verified. It happens quietly, without you noticing. And for decades, this has been enough. Long pause. But at the heart of all this, at the very foundation, is an assumption about difficulty, about time, about what is possible and what is not. And that assumption is this: certain problems are hard, not impossible, just hard. Hard enough. Hard enough that no one with any amount of computing power available today could solve them in a reasonable amount of time. And this assumption has held for a long time, through decades of scrutiny, of attempts, of mathematical analysis, but it is in the end an assumption, not a proof, not a certainty, just a very, very confident belief backed by an enormous amount of evidence and effort. Pause. Let's think about that for a moment. What does it mean for a problem to be hard? In everyday life, hard might mean difficult to understand, or physically demanding, or emotionally challenging. But in computer science, in cryptography, hard has a specific meaning. It means that the best-known algorithm for solving the problem takes a very long time. Time that grows not just linearly with the size of the problem, but exponentially, or superpolynomially. What does that mean? It means that if you double the size of the problem, say you double the length of the number you're trying to factor, the time required doesn't just double, it doesn't even quadruple, it explodes. It grows so fast that even the fastest computers, running for billions of years, couldn't finish the task, and so the problem is, for all practical purposes, impossible. Not theoretically impossible, just practically impossible. And that distinction is important, because it means the security of these systems isn't absolute, it's contingent. It depends on the continued difficulty of these problems. Pause. Take RSA encryption, for example. RSA is one of the oldest, most widely used public key systems. It's been around since the 1970s. It's built into countless protocols, devices, services, and RSA relies on a very specific problem, factoring large numbers. If I give you a large number, say, a number with 2048 bits, which is about 617 digits long, and I tell you it's the product of two prime numbers, can you tell me what those two primes are? In principle, yes. You could try dividing by every possible prime. You could use more sophisticated algorithms like the number field sieve, which is the best classical algorithm we know of. But even with the number field sieve, even with the fastest supercomputers on Earth, factoring a 2048-bit number would take an absurd amount of time, more than the age of the universe. And so, for now, RSA is safe. For now. Pause. The same principle applies to other systems. Diffie-Hellman key exchange, elliptic curve cryptography. These rely on related problems, discrete logarithms in large groups that are believed to be equally hard, equally intractable, and for decades this belief has been tested. Researchers have tried to find faster algorithms, they've tried to break these systems, they've analysed them from every angle, and the systems have held. Not because it's proven they can't be broken, but because no one has yet found a way to break them efficiently. And in the absence of a breakthrough, we assume they remain secure. Long pause. Now let's turn, slowly, to the other layer, symmetric cryptography. This is different, simpler in a way, less exotic. Symmetric encryption doesn't rely on hard mathematical problems like factoring or discrete logs. It relies on something more, direct, the sheer size of the key space. Imagine a lock with a trillion possible combinations. More even, a lock where trying every possible key one by one would take longer than the heat death of the universe. That's symmetric encryption. Algorithms like AES, Advanced Encryption Standard, use keys that are 128 bits long, or 192, or 256 bits. A 128-bit key means there are 2 to the power of 128 possible keys. That's a number so large it's almost meaningless to write out. Something like 340 undecillion. And if you tried to check every possible key, 1 per nanosecond, it would still take billions upon billions of years. And so, the security of AS isn't based on a clever mathematical trick, it's based on exhaustion, on the impossibility of searching that vast space. Pause. And this too has held for decades. AES has been analysed, attacked, tested. Researchers have tried to find shortcuts, ways to reduce the search space, ways to predict the key without trying every possibility. And while there have been minor improvements, tiny optimizations, nothing has come close to breaking AES in practice, not with recommended key sizes, not with proper implementation, and so this layer too remains secure. Pause. But notice the pattern. Both layers, public key and symmetric, rely on the same underlying principle: time, difficulty. The assumption that certain tasks take so long, require so much computational effort that they are effectively impossible. And this assumption has been the bedrock of internet security for as long as the internet has existed. Long pause. But what if something changed? What if a new kind of computer appeared? A computer that didn't just run faster, but ran differently. A computer that could solve certain problems, not all problems, but certain specific ones, in a fundamentally different way. A way that collapsed the time required from eons to hours. That's the question. The slow, careful question that has been building in the scientific community for decades now. Not a question born of panic, but of foresight, of prudence. What if quantum computers became real? Not science fiction, not theoretical curiosities, but actual functioning machines capable of running the algorithms that, on paper, could break these locks. What then? Pause. And the answer, again, is not catastrophe, not an immediate collapse, but a shift, a transition, a recognition that certain locks would need to be replaced, and that transition is already underway, slowly, methodically, without alarm. Let's drift a little further now, into the idea of quantum computers, not as something to fear, not as a dramatic arrival, but as a concept, a possibility, a machine that operates according to principles most of us will never fully grasp, and that's perfectly fine. You don't need to understand quantum mechanics tonight. You don't need to picture qubits or entanglement with any clarity. Just let the ideas wash over you, gently, like rain on a window. Pause. A quantum computer is not simply a faster version of the computers we use today. It's not a laptop with better processors. It's not a supercomputer scaled up another 1,000 times. It's something fundamentally different. A different kind of machine, based on different principles, operating in a different space of possibilities. And that difference, that fundamental strangeness, is what gives quantum computers their power and their limitations. Pause. Let's think about an ordinary computer for a moment. The device in your pocket, the machine on your desk. These work with bits, zeros and ones, on or off, true or false. Each bit is in one state at a time, definitely, concretely. And the computer processes these bits, billions of them per second following clear deterministic rules. This is classical computation, the kind we've been doing for nearly a century now. And it's extraordinarily powerful. It's built the modern world, it's connected continents, it's put satellites into orbit and rovers on Mars. But it has limits. Certain problems, certain kinds of calculations grow so large, so complex, that even the fastest classical computer would take lifetimes to solve them. And quantum computers, in theory, can solve some of these problems much, much faster. Not by working harder, but by working differently. Pause. The basic unit of quantum computation is called a qubit, a quantum bit, and unlike a classical bit, which is either 0 or 1, a qubit can exist in a superposition of both states at once. Not 0, not 1, but both, simultaneously, until you measure it, until you look, and then it collapses into one state or the other. This sounds strange. It is strange. It defies our everyday intuition about how things work. But it's not magic. It's physics, quantum mechanics, the rules that govern particles at the smallest scales. And these rules allow quantum computers to explore many possibilities at once, to interfere with themselves, to amplify correct answers and cancel out wrong ones. In certain problems with the right kind of structure, this gives quantum computers an enormous advantage. Pause. But here's what's important to understand, and you can let this settle slowly. Quantum computers are not universally faster. They don't speed up everything. They're not better at editing text or browsing the web or playing videos. For most everyday tasks, a quantum computer would offer no advantage at all. None. Their power is specific, targeted. They excel at certain structured problems that have hidden patterns, problems where interference and superposition can be exploited, and it turns out, and you can rest in this fact, that some of the hard problems underlying internet encryption are exactly the kind of problems quantum computers might solve efficiently. Not all cryptography, but certain pieces of it. The public key layer, the locks built on factoring and discrete logarithms, those locks specifically are vulnerable, in theory. Long pause. Let's talk about the algorithm that made this clear. It's called Shor's algorithm, named after Peter Shor, who discovered it in 1994. And Shor's algorithm is, in a way, elegant, beautiful even, though you don't need to understand how it works to appreciate what it means. What Shor's algorithm does is this. It takes the problem of factoring large numbers, the problem that RSA encryption relies on, and transforms it into a different kind of problem. A problem about finding periods, finding repeating patterns in sequences. And this new problem, this period finding problem, is something a quantum computer can solve efficiently. Not in exponential time, not in superpolynomial time, but in polynomial time. Time that grows slowly, manageably, as the size of the problem increases. Pause. Let's sit with that for a moment. What Shor's algorithm means is that a sufficiently large, sufficiently stable quantum computer could factor a 2048-bit RSA modulus in a matter of hours, or days, or weeks, not billions of years, not longer than the age of the universe, but hours. And if you can factor the number, you can break RSA, you can recover the private key. You can decrypt messages, you can forge signatures. The lock, in other words, would no longer hold. Pause. And the same principle applies to other public key systems, Diffie-Hellman key exchange. The protocol that allows two parties to agree on a secret over an insecure channel. That relies on the discrete logarithm problem, which Shor's algorithm can also solve efficiently. Elliptic curve cryptography, ECC, the modern efficient alternative to RSA and classic Diffie-Hellman. That relies on the elliptic curve discrete logarithm problem, which again Shor's algorithm can break. All of these systems, RSA, Diffie-Hellman, ECC, share the same vulnerability. They all rely on problems that quantum computers in theory can solve. Pause. But notice the phrase, in theory, and notice another word, sufficiently large, because here's the critical thing, and you can let this calm you. No such quantum computer exists today, not even close. Long pause. The quantum computers we have right now, the experimental machines in research labs, the devices companies are building, are far, far too small, too noisy, too fragile. They have, at most, a few thousand qubits, and those qubits are error-prone. They lose coherence quickly. They require constant correction, constant maintenance. Running Shor's algorithm to factor a 2048-bit RSA key would require millions of physical qubits, tens of millions depending on the architecture, and it would require those qubits to remain stable for hours or days. We are nowhere near that capability, not today, not this year, probably not for many years. Pause. Estimates vary. Expert reports suggest it could be a decade, 2 decades. Some say longer. Some say it might never happen. There is no consensus timeline. No one can say with confidence when, or even if, a cryptographically relevant quantum computer will be built. And so the threat is not immediate, not urgent, not a countdown clock ticking towards zero. It's a horizon, a possibility, a future that might arrive and for which we should prepare. Pause. And that preparation is already happening, not in response to a crisis, but as a careful, methodical process, a migration. Because even though large-scale quantum computers don't exist yet, there's a reason to act now. And that reason has a name. It's called harvest now, decrypt later. Long pause. Imagine this scenario. Imagine it slowly, without alarm. An adversary, a nation-state perhaps, or a well-resourced organization, is intercepting encrypted communications today, not breaking them, not decrypting them, just collecting them, storing them. Vast archives of encrypted data, emails, messages, backups, diplomatic cables, medical records, financial transactions, all encrypted with RSA or Diffie-Hellman or ECC, all secure, for now. But the adversary is patient. They're willing to wait. Because they know or they believe that one day a quantum computer will exist, and when it does, they'll take those old encrypted files out of storage and they'll decrypt them, not in real time, not immediately, but retrospectively. Secrets that were safe in 2025 could be revealed in 2035 or 2045. And for some kinds of information, state secrets, personal health records, long-term strategic plans, that's a problem. A quiet problem, a slow problem, but a real one. Pause. And so the recommendation from security agencies and researchers around the world is this. If you have data that must remain confidential for decades, you should protect it with quantum-resistant cryptography now. Not because the threat is here, but because the threat might be coming. And by the time it arrives, it will be too late to protect what's already been harvested. Pause. This is not just about confidentiality, though. It's also about authenticity, about trust, because public key cryptography isn't just used for encryption. It's also used for digital signatures, signatures that prove a message came from a particular person, or a particular company, or a particular government. Signatures that secure software updates, that authenticate websites, that underpin certificate authorities, the systems that tell your browser which sites are trustworthy and which are not. And if those signatures can be forged, if RSA or ECC signatures become breakable, then the entire trust infrastructure of the internet is at risk. Not just past secrets, but future authenticity. Pause. And so, the migration isn't optional. Not really. It's a necessity, a long-term project, one that will take years, perhaps decades to complete, but one that is already underway, quietly, methodically, without panic. Long pause. Let's turn now to the other side of the quantum threat, the side that's less dramatic, less alarming, the threat to symmetric cryptography. Pause. Remember, symmetric encryption, AES, Cha-Cha-20, and similar algorithms doesn't rely on hard mathematical problems like factoring. It relies on brute force, on the impossibility of searching an enormous key space, and quantum computers do offer an advantage here. But a much smaller one. There's another quantum algorithm discovered by Love Grover in 1996. Grover's algorithm. And what Grover's algorithm does is this. It speeds up unstructured search. If you're looking for a needle in a haystack, if you have to check every possibility one by one, Grover's algorithm lets a quantum computer do it faster, not exponentially faster, not a collapse from eons to hours, but quadratically faster. Pause. What does that mean? It means that if a classical computer would take, say, 2 to the power of 128 operations to break a 128-bit key, a quantum computer using Grover's algorithm would take 2 to the power of 64 operations. Still an astronomically large number, still far beyond what's practical, but smaller, noticeably smaller. Pause. And so the security margin is reduced. A 128-bit key under quantum attack effectively behaves like a 64-bit key classically, which is not ideal, but not catastrophic. Because the solution is simple, use longer keys, AES 256 for example, a 256-bit key. Under quantum attack, that would behave like a 128-bit key classically, which is still plenty secure, and so symmetric cryptography doesn't break. It just requires an adjustment. A doubling of key lengths, roughly speaking, a modest cost, a manageable change. Pause. The same principle applies to cryptographic hash functions, functions like SHA-256, SHA-3. These are used for integrity checking, for digital signatures, for various authentication tasks, and Grover's algorithm reduces their effective security by half. But again, the solution is straightforward. Use longer outputs. Use constructions designed with quantum adversaries in mind, and the system remains secure. Long pause. So let's pause here and take stock. Let's let this settle. What we've learned so far is this. Quantum computers, if they become large and stable enough, would decisively break certain kinds of cryptography. The public key systems based on factoring and discrete logarithms, RSA, Diffie-Hellman, ECCC. These would become insecure, vulnerable, unusable, but symmetric cryptography, AES Cha-Cha-20 hash functions, would only be weakened, and only modestly. They could be secured again simply by increasing key sizes. Pause. And so the internet would not fall over, not instantly, not completely, but certain foundational pieces would need to be replaced, and that replacement is happening now, slowly, carefully, through a process called post-quantum cryptography. Long pause. Post-quantum cryptography. Let that phrase settle. It's not cryptography that runs on quantum computers. It's cryptography that runs on ordinary classical computers, the devices we already have, but that is designed to resist attacks from both classical and quantum adversaries. New locks, new mathematical problems. Problems that, as far as we know, even quantum computers can't solve efficiently. Pause. And there are several families of these new systems, several different mathematical approaches. One is called lattice-based cryptography. It relies on problems involving high-dimensional geometric structures, finding short vectors in lattices, learning with errors, problems that are believed to be hard even for quantum computers. Another is code-based cryptography, based on error-correcting codes, on the difficulty of decoding certain structured messages. There's hash-based cryptography, digital signatures built from cryptographic hash functions, simple, well understood, quantum-resistant, multivariate polynomial cryptography, systems based on solving systems of non-linear equations over finite fields, and isogeny-based cryptography, involving elliptic curves, but in a different way, mapping between curves rather than working within a single curve. Pause. These are the candidates, the families, the new generation of locks, and for the past several years researchers around the world have been analysing them, testing them, trying to break them, looking for weaknesses, for hidden shortcuts, for vulnerabilities, and some have been broken, some have failed. That's part of the process, but others have survived, have held up under scrutiny, and a few have been selected for standardization. Long pause. The process has been led by NIST, the National Institute of Standards and Technology, a US government agency, but one that works with the global cryptographic community. In 2016, NIST launched an open competition, an invitation to the world: submit your best post-quantum algorithms, algorithms for encryption, algorithms for key exchange, algorithms for digital signatures, and researchers responded. Dozens of submissions, from universities, from companies, from cryptographers around the world. And over the years, NIST has been evaluating them, running them through multiple rounds of selection, analysing their security, their performance, their practicality. Pause. And now, in 2025, the first standards are being finalised. Algorithms have been chosen. For key encapsulation, essentially for agreeing on shared secrets securely, NIST selected a lattice-based algorithm called Crystal's Kyber, now standardized as ML-Chem. For digital signatures, they selected Crystal's dilithium, ML-DSCA, also lattice-based, and Falcon. Another lattice-based signature scheme, and SLH-DSA, a hash-based signature scheme. Pause. These are not experiments, not theoretical exercises. These are real, deployable algorithms, algorithms that can run on ordinary servers, ordinary devices, with reasonable performance, with acceptable overhead. Yes, the keys are larger, the ciphertexts are larger, there's a bit more data to transmit, and yes, there's a small increase in latency, a few % in most cases, but nothing catastrophic, nothing that would break the internet, just a modest cost for long-term security. Long pause. And deployment is already beginning, not everywhere, not all at once, but gradually, in stages. Some companies are integrating these algorithms into their protocols, into TLS, the protocol that secures web traffic, into VPNs, into email systems, often in what's called a hybrid mode, where both a classical algorithm and a post-quantum algorithm are used together, so that even if one fails, even if we discover someday that lattice problems aren't as hard as we thought, the other provides a backup, a belt and suspenders approach, cautious, prudent. Pause. And this is how the transition will happen, not in a single dramatic moment, not a flag day where everything changes at once, but slowly, system by system, protocol by protocol, over years, perhaps decades, as old devices are replaced, as software is updated, as standards are revised, a gradual migration, a long careful project. We're still here, still drifting through these ideas, still letting them settle like dust motes in a shaft of afternoon light. There's no hurry, no destination we must reach, just this slow unfolding, this gentle exploration of a future that is uncertain, but not frightening. So pause. Let's think for a moment about what we don't know, about the uncertainties, the open questions, because science is not a collection of certainties, not a finished cathedral. It's a process, an ongoing conversation, a landscape of questions, some answered, many still open. And when it comes to quantum computers and cryptography, there are many questions still waiting for answers. Pause. First, there's the question of when. When will a large-scale, cryptographically relevant quantum computer actually be built? And the honest answer is, we don't know. We don't know. Estimates vary widely. Some experts say 10 years, some say 20, some say 50, some think it might not happen at all, that the engineering challenges, the problems of scaling up, of maintaining coherence, of correcting errors, might prove insurmountable, or at least too expensive, too difficult, too impractical. Pause. Building a quantum computer is not like building a faster processor. It's not just a matter of making things smaller, or running them faster, or stacking more of them together. It requires maintaining quantum coherence across millions of qubits. Qubits that are exquisitely fragile, that lose their quantum properties at the slightest disturbance, heat, vibration, stray electromagnetic fields, even cosmic rays passing through the machine. All of these can cause errors, can disrupt the calculation, and so quantum computers require extreme isolation, extreme cooling, often temperatures close to absolute zero, and they require error correction, vast amounts of it. Pause. Error correction in quantum computing is not simple. You can't just make a backup copy of a qubit. Quantum mechanics forbids that, the no-cloning theorem. Instead, you have to encode each logical qubit, the qubit that actually does the computation, in many physical qubits, sometimes dozens, sometimes hundreds, sometimes thousands, so that when errors occur, and they will occur, you can detect them and correct them without destroying the quantum information. Pause. And this means that to run Shor's algorithm on a 2048-bit RSA key, you don't just need a few thousand qubits. You need tens of millions, and those qubits need to remain coherent for hours or days, long enough to complete the calculation, and we are nowhere near that capability today. Nowhere near. Pause. The largest quantum computers today have a few thousand physical qubits, and even those are noisy, error-prone. They can run shallow circuits, simple algorithms, brief calculations, but nothing on the scale required for breaking RSA or ECC. Not yet. Not for a long time. Long pause. And so there's uncertainty about the timeline, about when the threat becomes real. But there's also uncertainty about the defenses, about whether post-quantum cryptography is truly safe. Pause. Remember, the security of RSA and ECC was based on assumptions, on the belief that factoring and discrete logarithms are hard problems, and those assumptions held for decades. They've been tested extensively, but they were never proven, not mathematically. There's no theorem that says factoring must be hard. It's just, as far as we know, it is hard. Until Shor's algorithm showed that it isn't hard for quantum computers. Pause. And the same is true for post-quantum cryptography, lattice problems, code-based problems, hash-based constructions. These are believed to be hard, even for quantum computers. But that belief is an assumption, a well-studied assumption, a carefully examined assumption, but not a proof. We cannot say with absolute certainty that no quantum algorithm will ever be discovered that breaks these systems. We can only say, we've looked hard, and we haven't found one. And the problems seem fundamentally different from factoring and discrete logs. They don't have the same structure that Shor's algorithm exploits, but we cannot rule out the possibility of a breakthrough, a new algorithm, a new approach. Pause. And so the cryptographic community continues to analyze these systems, continues to attack them, to test them, to try to break them, not because they expect to succeed, but because that's how security is built, through adversarial thinking, through scrutiny, through the assumption that if something can be broken, it eventually will be. Long pause. There's also uncertainty about implementation, about how these algorithms will perform in the real world, on real devices, under real constraints. Because cryptography is not just mathematics, it's also engineering, and even a mathematically secure algorithm can be vulnerable if it's implemented poorly. Pause. Side-channel attacks, for instance. These are attacks that don't break the mathematics, don't solve the hard problem. Instead, they exploit the physical implementation of the algorithm. They measure how long the computation takes. Timing attacks. They measure how much power the device consumes. Power analysis attacks. They analyze electromagnetic radiation, acoustic emissions, even the heat generated by the processor. All of these can leak information about the secret key. Pause. And post-quantum algorithms, it turns out, are sometimes more vulnerable to side-channel attacks than classical algorithms. Not because the mathematics is weaker, but because the operations are more complex, more varied, more opportunities for leakage, and so implementing these algorithms securely requires careful engineering, constant time code, masking, blinding, techniques to hide the secret information from physical observation. Pause. This is especially challenging for constrained devices, smartphones, IoT sensors, embedded systems, devices with limited memory, limited processing power, limited battery life. For these devices, post-quantum cryptography is more expensive, more demanding, not impossibly so, but noticeably so, and so the migration for these devices will take longer, will require more optimization, more engineering effort. Long pause. But let's step back. Let's zoom out from these technical details and see the broader picture. Because the broader picture is actually quite reassuring. Pause. What we're witnessing is not a crisis, not a collapse, it's an evolution. Cryptography has always evolved, always adapted to new threats, new capabilities, new understandings. In the 1990s, when it became clear that DES, the data encryption standard, was becoming too weak, we transitioned to triple DES and then to AES. When SHA-1, a widely used hash function, showed signs of vulnerability, we moved to SHA-2 and SHA-3. When 10 to 24-bit RSA keys were deemed insufficient, we move to 2048-bit and 4096-bit keys. Pause. Each transition took time, years, sometimes decades. Each required coordination, standardization, testing. Each had costs, compatibility issues, performance overhead, but each was accomplished successfully, without catastrophe. And the quantum transition will be the same. Yes, it's more profound, more architecturally significant. We're not just increasing key sizes, we're replacing entire families of algorithms, but the process is the same: careful, methodical, incremental. Pause. And the process is already well underway. NIST's standardization effort has been running for nearly a decade. Other organizations, IETF, ISO, ETSI, are coordinating. National security agencies are issuing guidance. Companies are integrating PQC into their products. Academic researchers are continuing to analyze, to optimize, to improve. Pause. There are pilot deployments, real-world tests. Google has experimented with post-quantum algorithms in Chrome. Cloudflare has tested them on their networks. Banks are beginning trials for quantum-resistant financial transactions. Governments are planning migrations for classified communications, not because the threat is imminent, but because preparation takes time, and the prudent approach is to start early. Long pause. One concept that comes up often in these discussions is crypto-agility. Let that phrase settle for a moment. Crypto-agility. It means designing systems so that the cryptographic algorithms can be swapped out, upgraded, replaced, without rebuilding the entire system from scratch. Pause. Because one lesson we've learned from previous transitions is that hard-coded cryptography is fragile. If your protocol assumes RSA and only RSA, then when RSA becomes insecure, your entire protocol needs to be redesigned. But if your protocol is designed to be algorithm agnostic, if it can work with RSA today and lattice-based encryption tomorrow, then transitions become much easier. Pause. And so modern protocol designs emphasize this flexibility. TLS 1.3, the current version of the Transport Layer Security Protocol, is designed with algorithm agility in mind. It can negotiate which algorithms to use, can support multiple options, can be updated without breaking existing implementations, and this makes the quantum transition smoother, not effortless, but smoother. Long pause. Let's think about timelines again. Not the timeline for quantum computers. We've already acknowledged that uncertainty, but the timeline for migration, for actually deploying post-quantum cryptography at scale. Pause. Security experts generally recommend a phased approach. First, high-value targets, systems that protect long-lived secrets, government communications, financial infrastructure, health records. These should transition first, and many already are. Next, general enterprise systems, corporate networks, cloud services, major web services. These will transition over the coming years, gradually, as standards are finalized and implementations mature. Finally, consumer devices, personal computers, smartphones, IoT devices. These will transition last, over a longer timescale, as devices are replaced through natural upgrade cycles. Pause. The whole process will likely take a decade or more, not because anyone is dragging their feet, but because these systems are vast, interconnected, complex, because compatibility matters, because testing matters, because rolling out changes to billions of devices takes time. Pause. But by the time large-scale quantum computers arrive, if they arrive, the migration will likely be complete, or at least well advanced, and the internet will continue to function, not unchanged, but secure, protected by a new generation of locks built to withstand both classical and quantum adversaries. Long pause. It's worth noting too that quantum computers are not all threat, they're also opportunity. Pause. Quantum computers, if they can be built at scale, promise to revolutionize certain fields: drug discovery, materials science, optimization problems, simulating quantum systems themselves. These are areas where quantum computers might offer genuine breakthroughs, might help us design new medicines, new batteries, new catalysts, might help us understand complex physical systems that classical computers struggle with. Pause. And in the long term, the very long term, there's even a possibility of quantum cryptography. Not post-quantum cryptography which runs on classical computers, but actual quantum cryptography. Protocols that use quantum mechanical principles themselves to ensure security. Quantum key distribution, for instance, where security comes not from computational hardness, but from the laws of physics, from the fact that measuring a quantum system disturbs it, from the no-cloning theorem. Pause. These protocols are not yet practical at scale. They require specialized hardware, optical fibers or satellite links, quantum repeaters, but they exist. They work in principle. They've been demonstrated in labs and in limited deployments, and they represent a different vision of secure communication, one where security is guaranteed by nature itself, not by assumptions about computational difficulty. Pause. But that future is still distant, still speculative. For now, for the foreseeable future, our security will rest on classical cryptography, on post-quantum algorithms running on ordinary computers, on mathematics that we believe, with good reason, to be hard. Long pause. Let's return once more to the heart of all this, to the question we started with. Would quantum computers break the internet? Pause. And the answer, you can rest in this answer, is no. Not in the way that phrase might suggest. Not a sudden collapse, not a catastrophic failure, not darkness spreading across the digital world, but a challenge. Technical challenge, a mathematical challenge, one that requires certain systems to be upgraded, certain algorithms to be replaced, one that requires foresight, planning, coordination, but one that is being met, one that is, even now, being addressed. Pause. The internet is resilient, adaptable, it has weathered changes before, will weather changes again, and cryptography, the invisible skeleton that holds it all together, is evolving, as it always has, as it always will. Long pause. There's something almost poetic about this, about the way security is not a fixed state but a process, a dance between attackers and defenders, between capability and protection. For decades, the hard problems of factoring and discrete logarithms kept us safe. And now, as new capabilities emerge, or might emerge, we design new problems, new locks, lattice problems, code problems, hash-based constructions, problems that seem, as far as we can tell, to be hard even for quantum computers. Pause. And perhaps, one day, those will be threatened too, by some new computational paradigm we haven't imagined yet, by some breakthrough we can't foresee. And when that day comes, Cryptographers will adapt again. We'll design new systems, new problems, new locks, because that's the nature of the field. That's the nature of security in a changing world. Long pause. And so we find ourselves here, at the end of this long, slow exploration. We've talked about locks and keys, about problems that are hard and problems that might become easy. We've talked about RSA and ECC and AES, about Shor's algorithm and Grover's algorithm, about qubits and superposition and interference, about harvest now, decrypt later, about NIST standards and lattice-based encryption, about timelines that are uncertain and migrations that are already beginning. Pause. And through it all, one theme has remained constant. The internet will not fall over. Cryptography will not collapse. There is no crisis, no countdown, no sudden end, just a long, careful transition, a methodical upgrade, a migration from one set of locks to another, from problems that quantum computers can solve to problems that, as far as we know, they cannot. Pause. And that transition is happening now, not because quantum computers are here, but because they might be coming, not out of panic, but out of prudence, not in haste, but with care. Long pause. So if you're lying here, listening to this, wondering whether your bank account is safe, whether your messages are private, whether the digital infrastructure we all depend on is about to crumble, you can rest. You can let that worry go. The people who build these systems, who study these problems, who standardize these protocols, they're thinking ahead, they're planning, they're testing, they're deploying, and by the time quantum computers arrive, if they arrive, the work will be done, the new locks will be in place, and the internet will continue, secure, resilient, different perhaps in its internal workings, but fundamentally the same in what it provides: connection, communication, trust. Long pause. Cryptography is, in the end, a story about trust, about how we create spaces of privacy and authenticity in a world where information flows freely, about how we build systems that protect what matters even as threats evolve. And that story continues, not because we've solved every problem, not because we've eliminated every risk, but because we've learned to adapt, to evolve, to stay ahead of the curve. Pause. And so the internet, that vast web of connections and protocols and trust, will endure, will adapt, will continue to connect us, to serve us, to enable the modern world, even in a quantum era, even as computation itself changes shape. Long pause. And with that thought, you can rest, let it all drift away, the qubits and the algorithms, the timelines and the threats, the lattice problems and the error correction, all of it. Just rest. The world is being taken care of, the work is being done, and you can simply be here, breathing, still, at peace. Very long pause. Sleep well.